We embark now on the second half of calculus, the part dealing with the integral of a function. The first half of calculus was about the derivative of a function, and that dealt with the large problem of what is a tangent line and how do you find it. And you saw what that led to. Now we're going to ask the question, what is area and how do you find it in general? And then the word integral will be defined at that point. So we will begin here by looking at the question of area. And the very first thing we'll talk about is a brief history and overview of the question. From your own past, you know some area formulas. For example, if I draw here a rectangle and I ask you what the area of this rectangle is, supposing it has dimensions a by b, then you would probably write down that the area is equal to a times b. In fact, this is a definition of area, and area itself is attaching a number to this region somehow. And there are different ways to define area, but of course this is the traditional way, and we'll start with that. Then, of course, if I asked you for the area of a triangle, maybe a right triangle like this, and here's A and B, and I said, what is the area here? And this works for any triangle, but the picture I've drawn is a right triangle. Then the area is always 1/2 the base, that may be the way you've learned it, the 1/2 the base B times the height, which is vertically measured, A. So it's 1/2 AB. And so on. Once you have rectangles and you have triangles, you can do the areas of other polygons. And there's really not much difficulty in coming up with those areas. However, when you start asking questions like, what is the area of a circle? There's a center of the circle, and we're asking what this area is. Then we have difficulty. This is a curved region. How do we use what we know about the straight line regions, the rectangles, and the other polygons, the triangles and so on, to get the area of the circle? Well, a long time ago, Archimedes found a way to do this. And just for the record, he lived about 287 BC to 212 BC. And he used what we now call the method of exhaustion. And he's not the only one that used this, but he's well known for this. And so if you were looking for the area of a circle like this, what you could do is say, well, I don't know the area of the circle, but I can inscribe in here a regular polygon, say an equilateral triangle, and I do know how to find the area of that. And this is inscribed, so it's touching at all three of its vertices. Then I might extend that and say, well, if I were looking for the area of a circle, I could do better than that. I could draw in here a square that is inscribed and touching at its four corners, and I know how to find the area of the square. And I could continue that process if I wanted. I could move up perhaps to a pentagon, a five-sided figure, and I'd see that this area will approximate the area of the circle even better than the square and the triangle did. And I can imagine this property going on forever, and that eventually the polygons in here, the areas of these polygons would exhaust the area of the circle. And if I were allowed somehow to go to infinity, which is a question in itself, I could get the area of this curved region. And Archimedes did it that way. He went from the inside and he also went from the outside by drawing polygons that surrounded a circle and making them fit better and better, and ended up with a formula for the area of a circle, which you all know. So in this kind of a situation, the area of a circle turned out to be, and I'll use our modern terminology, the limit of the areas of polygons. Whether they are polygons as I've drawn that are inscribed or ones that are circumscribed, this would be thought of as a limit that way. But that still raises lots of questions. This is only one curved figure. There are many curved figures. So one could ask, what about regions that are completely irregular? Like maybe this thing. How would I find the area of that? Well, if I'm going to do this, I'm going to need a theory that's more general than what I have here. So we will attack that as the calculus does at this point, and we will limit ourselves to a particular area problem, which then will generalize to all the cases like the drawing I just made. The area problem we will limit ourselves to. So the area problem we will address in this environment is exactly the following. We have to work with what we've already developed, and then we'll go from there. Imagine that we are on the axis system, and we have some kind of a curve here. So here is a function, and we will suppose that this function is continuous as our first step, and we will also suppose that this function is greater than or equal to 0, as I have drawn it. Its picture is above the x-axis. Then suppose we move between some point A here on the x-axis and some point B here. The question we want to ask is, what is this area? Now, this is a fairly irregular area, but it at least has the advantage of being like a rectangle vertically and horizontally here at the bottom. So it's like three sides of a rectangular type figure and then just a curve here. If we can solve this problem, we'll be able to solve the general area problem. So the question then here is, what is the area between the graph of f, as I've drawn it, and the interval on the x-axis? So that here is the interval AB on the x-axis. What is this? How do we figure out this area? What techniques can we use? Well, the idea is going to be to get organized, not just to randomly try to figure polygons that fit in here and finding some sort of a limit, because that would then depend on whatever the function is. We want to have something that's going to work for all sorts of functions. So here is the first method that we will examine. We'll call this the rectangle method, because rectangles are about as easy as you can get if you're looking for area. The rectangle method for finding such areas. That's areas as I described on the previous page between the graph of a function and the x-axis. So here's the idea, so that we can get rectangles into the picture. The picture we had was maybe some kind of a function like this, going between a and b. So this is my function f of x, and we want to find this area in here. Here's what we'll do. We will divide this a to b interval into parts. So divide into n equal subintervals. Now, for the sake of this picture, I'm going to just pick an n size. Let's see. How about if we break it up into 6 equal parts? So I'll make that note here. Here n is equal to 6. But it could be any number of equal subintervals. And later we'll even find out that they don't have to be equal. The same results that we're going to get here will work even if they're not equal. But for now, divide it into n equal subintervals, and here I've got 6. Then the next thing we'll do is we will slice the area vertically. So what I mean is, from each one of these places where I have divided the interval, vertically go, in this case, upward to the curve, and slice the area up into these 6 regions. Now, these regions are not rectangles, but they're not too far off from rectangles. They're really different from rectangles only because of their tops. So if we could rectify that, we'd have a rectangle appearing in each one of these regions. So here's what we do. We take, and I'll just do this one at a time. Suppose we have a piece of the curve here, and here is a slice, say, and I've enlarged it a little bit. Now I want to get a rectangle associated with this, so I really need to decide where I'm going to put the top of the rectangle. How do I do that? Well, what I do is I pick any point whatsoever in this little subinterval. So let me mark that here. Choose any point to determine the height, or determine a height. So what I mean by that is, I have this point and I will draw a vertical slice above that point, and notice it's going to strike the curve somewhere. I will use that point as the indicator for the top of the rectangle. So then I will have a rectangle then that looks like this, where this is the height I just discussed. And of course, the width here is the width of the base of the rectangle, which is the same as all these others. So with those two, I can find the area of this rectangle, and that's where I want to head next. From here, I will then have my rectangle And I'll draw it a little more cleanly here. Maybe it sits here something like this. There's the point where I've got my top, and here now I have a rectangle. So this rectangle is associated with the curve because I use the point down here to come up here and take the top and make it cross the curve. But the point could be anywhere. It could be the left, the right, the middle, or any point in between. Now it's clear that this rectangle is not the correct area under the curve. See, this rectangle is a little bit too high. If I shade this in, you can see it's too much. And on the right-hand side, it's too little. But this is going to be a start toward getting the actual area under the curve. And to see that a little better, now we'll look at a visualization. Here you see we have a curve drawn, and here are a couple of rectangles. Now it doesn't look like much because there are only two rectangles. One thing you should note about these rectangles is that they are touching at their left endpoint, which means the point that was chosen down here on this interval, which goes from 0 to 1 in this picture, was at the left endpoint, and we were uniform in doing that. So if you do it for this rectangle, you see there's no height. Let's increase the number of rectangles to 4, and now it looks a little better. We're still at the left endpoint, so there's nothing here, and then there's this rectangle, this one, and this one. If I continue to increase the number of rectangles, notice how the area under the curve is gradually being approached by these rectangles. And once I get to 32 here and beyond, it looks like I've almost filled in the entire area. Let's now go back to a smaller number and switch to a right endpoint touching rectangle. Now each one of these rectangles, notice, touches at the right endpoint. See, there's the right, there's the right, there's the right, and there's the right. And that makes these rectangles for this particular curve stick up outside the area of the rectangle. But let's increase the area, increase the number of rectangles, and see what happens. Notice that the more rectangles I get, the better and better fit I get. It's still too much, but the fit is better. And if I increase them again, the fit is even better. And once again, when I get up to 32, the fit looks pretty close to the actual area under the curve. And as you increase this more and more, you'd see that it fit even better. One more time, let's go back to a small number of rectangles, and now let's go to make them touch at the midpoint. So each one of these rectangles is now touching the curve at the center of the rectangle. So that means the point down here in the subinterval was the midpoint. And we came up here and touched the curve and used that as the top. So these stick out a little bit here and then are not quite high enough to fill this part. Same thing here, a little bit out, a little bit in. And because of the nature of this curve, it looks like this might be a better fit. So let's increase the number of rectangles, and then yet again. You see how much better this is fitting than either of the ones before, but still it's not perfect. And if we increase to 32, we see that this looks very, very close, just as the others did. So this is the idea behind the rectangle approximation process that we've just learned about. The fact that I will now increase even more. There's 64, there's 128, and now you can't even tell the difference between the rectangles and the actual area under the curve. Whereas if we went all the way back down to the early ones, like 2 for example, they are very, very crude. So the more rectangles, the better the fit, as long as the rectangles are somehow associated with the curve. So as we just saw, as n, which is the number of subintervals, or in the number of rectangles, as that number, and I'll write it out, this is the number of equally spaced rectangles, as you saw in the previous set of images. As n, the number of equally spaced rectangles, increases, it seems, and the picture is certainly suggestive, it seems that the total sum of the areas of these rectangles, so we take all these rectangles, which are all approximations, and we add them all up, then that total sum seems to be heading toward, under a limiting process of some kind, the area between the graph of f and the interval on the x-axis, AB. So that's what seems to be happening from our previous visualization. And that would be the rectangle area method of finding the area of those regions. Now let me mention a second method. And this is one we can't get to for a little bit, but it's worth introducing just so you know what's coming up. Another method for finding such areas is this one. Another method for finding such areas. Here's the idea. And this was something that was worked out by both Isaac Newton and Leibniz, the two co-founders of calculus. Suppose you have a function like this. So here is a function, I'm just going to call it f here. And we are again looking between an a and some other point, but I'm going to call this point here x instead of b. And we are interested in this area here, just as we've been looking at. Now I'm going to call this area a of x, and make a note that this is a function that changes as the x changes. If the x were to move this way, the area would change. The x moves this way, the area would grow. So certainly this is a function of some kind. And notice too that right at the point x, this is the height f of x. That's what f of x means. So here a of x is equal to the area indicated, that means shaded here, over the closed interval a to x. Now, with that notation set up, we'll see later, and this will be a primary subject for us coming up, we'll see later this remarkable fact. The remarkable fact that if you take this area function and you take its derivative, so a prime of x, you turn out to get f of x, the function which is the boundary curve at the top. So the derivative of the area turns out to be the function that helps create that area. This is a very important fact that Newton and Leibniz discovered, and this allows you to find area. So this is how you would do it. If we knew, and of course we'll have to learn how to do this, if we knew how to undo a derivative, and here that would mean to undo this derivative, because we have f of x, which means we have the derivative of a. If we could undo it, we could get back to a, which is the area under the curve that we're looking for. If we could undo a derivative, we could find a of x. So that will be something else that we'll be looking at as time goes on. And that's the end of this brief overview.